we're going to talk about exponential and logarithmic equations, okay? And functions, okay? So it's going to be a little bit of both. Okay, so let's go on to talk about first an exponential function. Okay, and I do want you to remember what these look like, okay? This was one of the parent, on that parent graphs page, we did talk about some exponential functions. And so they look like, I'll just make one up real quick, b to the x power. So b is going to be between 1 and just whatever, doesn't matter. Okay, and so depending on the base, the graph will look something like this. Right, so it may be very steep, it may not be so steep, okay, but you'll notice a couple things. First of all, it has a horizontal asymptote. You can zoom in and see it doesn't actually ever touch the x-axis, but it gets close to it. So just by looking at the graph, you can determine that that the domain goes from negative infinity to positive infinity. Okay, it's going to drift this way to the right forever. Even though it does kind of grow pretty quickly, it still drifts to the right forever. Okay, so that's the domain. The range, though, goes from 0 to infinity, 0 to infinity. Okay, and so this notation here, f of x equals a times b to the x. This part right here is really the exponential term. This is just a coefficient in the front that can help adjust it, make it, you know, just flip it over, make it steeper, turn it around. Yeah, you could do a lot of stuff with the coefficients. Okay, so b is the base of this exponential function, and we just looked at the graph, but we saw that the domain was negative infinity to positive infinity. The range was 0 to infinity. Okay. All right, looks something like that. Okay. Okay, so let's work out this function right here. Let's find several things. The first thing we're going to look for is the sketch of the graph. Okay, and so when we look for the sketch of the graph, we're going to, I would recommend that we take into account what the graph generally looks like, which is something like this, and find the intercepts. Okay, at least find the y-intercept. Remember, the y-intercept occurs when you plug in 0 for x. So if I plugged in 0 for x, that's going to be y equals 5 to the 0 plus 1 power. That's just 5. Okay, so 0, 5. All right. Also, remember, we talked that they have a horizontal asymptote, right? This is the horizontal asymptote. It crosses at 0, 1, 2, 3, 4, 5. So it looks something like that. Okay, and so from this graph, I can determine the domain is negative infinity to positive infinity, which we kind of already knew that, but you know, let's write it out. It goes forever to the left and forever to the right. So we'll say the domain is negative infinity to positive infinity. The range, back to the graph here, goes from down here, 0, forever upward. So from 0 to infinity. All right. Okay, let's solve this equation here. So we did talk about exponential and logarithmic equations. So we'll talk about this one here. We did mention before we discussed logarithms, but remember, exponential and logarithmic expressions, they're inverses of each other. Okay, and so what I want to do is eliminate this 5 by using log base 5 on both sides of my equation. Log base 5 of 5 to the 2x plus 1 equals log base 5 of 10. Okay, if I do that on the left side, then that's going to cancel out nicely to leave me with 2x plus 1. On the left side, on the right side. All right, this is a value. Let me use the change of base formula to rewrite that. Okay, so change of base formula says if you don't remember, it's natural log or log base anything of the inside of the function number over the natural log of the base. I like to use natural log, but you don't have to use that. You could just use log or any other number you want, right? It doesn't really matter, but you typically want to go with natural log or log. Okay, I'm going to subtract 1 from both sides. And then I'm going to divide both sides by 2. When you divide a fraction by a number, it's the same thing as just putting that number in the denominator. Okay, so I'll do that. And then minus 1/2 there. So that'd be the exact value. I could type that in the calculator to get a decimal if I wanted to, but that's usually not what they want you to do. They usually want it written in this form. All right. Okay, let's solve this equation here. Okay, I could use the log of 5 on both sides or even log of 25 on both sides, but I spotted right away that this 25 here is the same thing as 5 squared. So I want to rewrite 25 as 5 squared. The reason I want to do that is because now my bases are the same. And remember, when you raise a power to a power, you just multiply them together. So that'd be 22x there. So 5, 2x plus 1 equals 5 to the 22x power. Okay, now if I apply that logarithm rule to both sides, log base 5 on both sides, those cancel. Forgot my equal sign. Those cancel and to leave me with 2x plus 1 equals 22x. Okay, I can solve that pretty easily. It's a regular old equation there. I will subtract 2 from both sides. Then I'll divide both sides by 20. So 1 over 20. 1 over 20. Okay, so those are exponentials. Let's deal with logarithmic functions. Okay, so here we have a logarithmic function. Okay, and this is a generic one here, log base b of x, where b is the base. Remember, logarithmic functions are inverses of exponential functions. Okay, they're inverses of each other. They're 1-to-1, so that means that they have an inverse, right? And so you can actually see this here. That's all this is saying. Log base b of x has an inverse function, which is b to the x. Okay, and so what do these graphs look like? So we can discuss the domain. Okay, oops. There we go. Okay, so depending on the base, of course, you'll have a different graph, but they're all going to have the same general shape here, right? Okay, this is a good one that you can visualize here. Okay, so notice, because it's the inverse of the exponential function, b to the x, its domain is going to be the range of b to the x. Okay, it's going to be the range of the exponential. So if the range of the exponential was 0 to infinity, because it kind of has a horizontal asymptote at 0 and then it goes up forever, Well, instead of having a horizontal asymptote, it will have a vertical asymptote. See, it never crosses it. It's close, but never crosses it. So that would be the inverse domain from 0 to infinity. And the range would be, well, down forever, negative infinity. And it ever so slowly, even though it doesn't look like it, it drifts upward forever. Hard to see it, but it's every few steps, it's a little bit higher, a little bit higher, a little bit higher. Okay, so the domain we just said is the range of an exponential, which would be 0 to infinity. The range is negative infinity to positive infinity, even though it takes forever to get up that high. That's the range. Okay, so here is a problem. Let's work this one out. Let's sketch the graph. We have an idea of what the general graph looks like. Looks like that. Okay, we know it's going to have a vertical asymptote somewhere. And also that the domain, so let's deal with that. The domain, it's going to have to depend on this inside piece. So something about logarithmic functions, the interior has to be a positive number. Inside has to be a positive number. So 3 minus x must be greater than 0. Or 3 must be bigger than x. Let's flip that around so it makes more sense. X has to be less than 3. Right? If 3 is bigger than x, then x is smaller than 3. Okay, so the domain is going to be from negative infinity to negative 3. Let's picture that on the graph. Negative 3 right here is the cutoff. That's where my vertical asymptote is going to be. And my graph has to stay on the left side. So it's going to actually be like that. Okay. You could also think about it as it is reflected horizontally and moved, since that's a positive 3, to the left 3 units. Okay. All right, so there's my sketch of the graph. Just from that, you can see that the range is going to be, again, negative infinity to positive infinity. Nothing's really going to change that. Okay, we're moving along quickly. Okay, let's solve this equation. So log base 5 of 3 minus x is equal to 4. Okay, so I want to do like we did in the other problem. Remember we added that log base 5 to both sides. Okay, I'll do the same idea. So the idea was that we added log base 5 because then log base 5 and exponential base 5 will cancel out. Okay, but if I already have a log base 5, what I could do is make the left side and the right side of the equation my exponents, and I'll make 5 the base. So this becomes my exponent. This becomes my exponent. Okay, so the benefit of that, exponential term, log base 5 cancels each other out. I'm left with 3 minus x. 5 to the 4th power, that's 5 times 5 times 5 times 5 is 625. Subtract 3 from both sides. 625 minus 3 is 622. Divide both sides by -1, and I get negative 622. Okay, I want to be careful with that solution because remember, we said that the inside of a logarithm has to be a positive number. So if I plugged in negative 622 into the logarithm, well, the two negatives become a plus. That becomes log base 5 of positive 625. Okay, this works out. So we don't have any issue there. So negative 622. Okay, here's the last problem here. We're going to finish this section early. Log base 5 of 3 minus x equals 2 minus log base 5 of x plus 9. I want to work this out. So I want to get x by itself. So the first thing I'll do is put the two logarithms on the left side by themselves. I'm going to add this log base 5 of x plus 9 to both sides. And it's good to remember our logarithm rules, right? Our properties. Because if you add together two logarithms with the same base, you can write them together as one logarithm, where the interior are multiplied together. Okay, I'm adding two logarithms together, so I can write it as one log with 3 minus x times x plus 9 inside. Okay, well, let me go ahead and get rid of the logarithm. I will make what we have, the exponent. Okay, that's a pretty complicated exponent, but there's that exponent. That one's easier. Those cancel out to leave me with 3 minus x times x plus 9 equals 5 squared is 25. Distribute. Okay, and now I need to solve a quadratic. So if it's a quadratic, let's combine like terms first. Negative x squared, 3x minus 9x is negative 6x, plus 27 equals 25. Okay, and there's a couple of options. I like completing the square here. This is not a factorable problem, so we're going to complete the square. To do that, I'm going to start off by moving the constant over, subtracting 27 from both sides. 25 minus 27 is negative 2. Next, I need to get this to be a positive 1 here, so I'm going to divide everything by negative 1, which just makes all my negatives positive. Okay, now to complete the square, you take the center number there, divide it by 2, and then square it. So 6 divided by 2 is 3. Square that is 9. So I'm going to add a 9 to both sides. As long as you add to both sides, everything's good. Okay, so the point of doing that allows this to factor as x plus 3 squared. The 3, by the way, is the same 3 that you get when you divide 6 divided by 2. 2 plus 9 is 11. So I have something squared equals 11. The square root property says that I can take the square root of both sides as long as I put a plus and minus in front over here. So that'll give me x plus 3 equals plus or minus the square root of 11. And so x equals, subtract 3, negative 3 plus or minus the square root of 11. Okay, so now of those, right, of those solutions, I have to make sure that plugging them in does not cause me to have a negative or a 0 inside of my logarithm. So I need to check them both, right? So it's easier if you find decimal approximations. I'll just type that in the calculator. This one is about 0.32. And this one is about negative 6.32. It's a 0.32 and negative 6.32. So we want to compare those with being plugged into the original equation. If I plug in 0.32 right here, 3 minus 0.32 will not be negative. It'll be a positive number, so we're good there. And of course, if I plugged in 0.32 here, 0.32 plus 9 will still be positive. 0.32 is good. If I plug in negative 6.32 here, 3 plus 6.32 would be 9.32. Okay, so that's positive. Negative 6.32 added here would give me a positive as well, right? Because negative 6.32 plus 9 is still bigger, so you'll still result with something positive. So, okay, both of them worked just fine. So there are my two solutions. All right, so there we go. That is whatever section this is, 18. And I guess I'll stop recording now.